beautiful thousandths place. Now, as you can see, my calculator's disappeared here, so I don't know what the number is, so I'm going to find the calculator real quick and punch those numbers in. Sorry about that. So, 0.500 minus 0.0185. Now this is going to give us 0.4815, and writing it properly, we're going to put 0.482 molar. We now have the concentration of our HF, our hydrofluoric acid, to end. So now what we can do, we can now plug this all in to find out what Ka is equal to. So Ka equals, if you remember, it was our hydronium ion concentration times our fluoride ion concentration, which is going to be the exact same concentration, divided by our new hydrofluoric acid concentrations. Now I'm writing HF, I need to put a number there. Try again, here we go. 0.482 molar. So I'm not going to pull up the calculator, I'm just going to do it on my own. So if you'll please do it with me. Alright, plugging them in. And what do we get for Ka? Ka is equal to 3 significant figures. I get 7.10 times 10 to the -4th. So, what does that all mean? Well, this is the Ka value, and you're going to probably like this a lot because Ka values, all right, they do not have units, so don't have to worry about a unit here. All right. You might want to pause this right now and look back over what you did, and we're going to move on to another problem and do some more steps with this. All right, we have practice problem number 2. If you want to pause here, you can try this out and then plug yours in and see what I get and compare the two. If you want to keep on going and don't want to do that, then just watch along. If you need a little more practice, you want to see me doing it. So here we go. Practice problem number 2. If 0.315 molar solution of nitrous acid dissociates and the new concentration is HNO2 of HNO2 is 0.303 molar, calculate the Ka for or of nitrous acid. Now, you're going to notice here there is no lovely Gauss equation, so we need to do that really quickly. So here we go. We have our lovely nitrous acid. Let's add it to some H2O. Again, if I'm asking you to calculate the Ka value, it's going to mean it's going to be a weak acid here. So what are we going to make? Well, once again, we make our hydronium ion, and we make a most lovely, let's see here, we're going to have the nitrite ion floating around. All right, so here we go. Let's see. Let's write our equilibrium, our Ka value, equilibrium expression. So we have Ka equals our products on top, so H3O plus and our NO2 negative over our reactants, HNO2. And a reminder, we will not put the H2O in there because, again, it's a pure substance, and we won't write those here. Now, let's write down some of our givens. What are we given here? Well, we're given the solution of nitrous acid at the beginning, and we're given the new concentration. So, we know our new concentration is HNO2 of nitric acid. Our new one is 0.303 molar. We like that. All right, so I'm also given the old one, which we don't plug into Ka. So right now, we don't have the hydronium ion concentration or the nitrite ion concentration. So how do you figure it out? Well, if you remember back to the last one, to find the new concentration for our reactants, right? What we had to do is we took the original concentration minus the hydronium ion concentration. Well, we don't have the hydronium this time, but they did give us the original 0.315 molar. We don't know how much it broke into, but we do know that we end up with a 0.303 molar solution. So we can easily solve for this. We can add x over to the other side and subtract the 0.303 over, so 0.0. Oops, not 0.0. Sorry about that. 0.315 molar minus 0.303 molar is equal to x. So, hopefully you don't have to plug that into a calculator, but if you do, that's quite all right. You can check yourself there. And we get x equals 0.012 molar. Now, what does that mean? Well, not only is this the hydronium ion concentration, but it's also the nitrite ion concentration. With that being said, let's plug in. Ka equals our value we just got for our lovely hydronium ion. Same value for the nitrite ion. All divided by, well, our nitrous acid concentration at the end, which we're told is 0.303 molar. So, our Ka value for this, let's plug it in, 0.012. And two of those, so we'll square them, divided by 0.303. And you should get 4 points. And with this, we only have 2 sig figs here, so it's going to be 4.8 times 10 to the negative 4th. And this is our Ka value for nitrous acid. All right, one more practice problem to do here to be ready for class tomorrow. This time we're going to do the ammonia solution. Well, if you remember, ammonia is not an acid, it's a base. So we're going to do Kb values. But the good news is Ka, Kb, exact same thing. All right, we're doing the same stuff. The only difference is we're dealing with the base. And instead of having that hydronium that's formed every time, we're going to have our hydroxide that's going to be formed. All right, so our hydroxide is going to be formed every time. So looking at this one, we have the ammonia solution as a Kb value of 1.9 times 10 to the negative 5th. If the hydroxide ion concentration is 2.9 times 10 to the negative 3rd molar, determine the original concentration of the ammonia solution. So if you want to try this on your own, you can pause it and come back to us. If not, you can just keep it playing and watch what we do. So first thing we need, let's write down our formula. Ammonia is NH3. All right. And our lovely ammonia is going to get into some water. I'm going to go back and talk about just those copies. We'll keep with that. The NH3, which is our dissolving some. All right, plus H2O. Alright, this is going to be a weak base for a double arrow. Alright, yields. We're going to make NH4 positive. That's the ammonium ion. Plus, I don't know why I'm putting the bracket there. Plus our hydroxide ion. Alright. With that said, let's write our Kb real quickly. Our Kb is equal to our reactants. We have our ammonium ion. I'm sorry, our product, not reactant. Correct that, our product. And our hydroxide ion, all over now our reactants. Our ammonia. All right. Let's see what we got. Now, this time's a little unique. I gave you the Kb value this time. So we know what the Kb is. It's 1.9 times 10 to the negative 5th. I also tell you, all right, that the hydroxide ion concentration is equal to 2.9 times 10 to the negative third molar. Well, remembering back, if we know the hydroxide, then I also must know my NH4 plus my ammonium ion, because however many hydroxides form, that's how many ammonium ions form, so it has to be the same here. Alright, well, we got all variables except one, so let's plug into our equation. This time they give me KB, so 1.9 times 10 to the negative fifth is equal to 2.9 times 10 to the negative third times same thing. And don't let our gibbons over here get in the way. Right, so divided by. Right, we do not know what our ammonia concentration is. So to solve this, we need to multiply our NH3 over and divide the 1.9 times 10 to the negative fifth over. So here we go. We have our NH3 over here is now equal to our 2.9 times 10 to the negative third molar times our 2.9 times 10 to the negative third molar. A faster way, you can just square that since you're multiplying the same number of times each other. Divided by 1.9 times 10 to the negative fifth. All right, so I'm going to plug this into my calculator. All right, so now I'm going to divide that by 1.9. And what do I get? I get NH3 is equal to, and I only have 2 sixteenths here, so it's a 0.44 molar. Now, I have to be very careful here. Remember that this is the concentration once it reaches equilibrium. When you put it in and it kind of mixes up and some of it dissociates. The original question asks, determine the original concentration. So, how do I determine my original concentration of it? Well, if you remember, all right, your final concentration is the original minus the ion concentration it forms. So, in this case, since we're dealing with the base, it's the original NH3, which we don't know, minus our 2.9 times 10 to the negative third molar is equal to our 0.44 molar. All right, simple enough. Our original concentration of NH3 is 0.44 plus 2.9 times 10 to the negative third. Now, fun thing happens here, as we all love sig figs. When I add this, if I rewrote 2.9 times 10 to the negative third, what I'm really doing is adding 0.0029. Now, the 0.0029 goes to the, let's see, 10,000th place. Here, our ammonium ion concentration that we have right now, or ammonia, only goes to the 100th. So when we add these, we actually just end up with the exact same number. Trust me, that is okay when doing Ka values, or Kb in this case. So our answer here is 0.44 molar of our original ammonia. And that's how you do it. If you have questions, write them down, and I'll take them in class.